you, Vincent. Thank you for having me. Well, I managed to come despite both the strike and the snow, so I'm quite happy to be here. And well, so I'm going to talk about something that is more probability side of things, so I hope it's going to be okay for you. So Gerard told me it's fine, so please don't throw tomatoes at me. And I'm going to talk about something that I'm really interested in, like this injective norm of random tensors, which I started to look at like 2 years ago, and I have a bunch of questions about it. And I'm just going to discuss here recent results that I obtained with Benjamin McKenna, who is at Georgia Tech. And you can find this result on this archive pre-publication, which hopefully is going to be reviewed soon. 4, 0, 3, 6, 2, 7. Okay. So the plan is to start with an introduction, in which I'm going to state the main result, and I will explain what is this injective norm. Okay. Then I will give ingredients of proof. Proof ingredients. And well, I hope I'm not too optimistic about the time, because usually I'm doing this in 1 hour. Sorry?
Proof of the introduction.
No, it's proof ingredients of the main result, you know. So if you want, I add and main result.
I think you have a little bit more time because it's the speaker disappeared.
And well, and if I have time, so as Maxime just said, I might have more time, so it's the advantage of being last. I will talk about the some context in quantum information. So finally, it has to do with complexity class, which I know almost nothing about. So Joseph, please help me. Well, and maybe conclude on something that I like to do later. Okay, so maybe I want to do this now. Okay, so let's start with the first part. So 1. So what am I going to talk about? So first, I will tell you about tensors. So I hope that you don't need too much introduction to tensors, because I'm going to be super fast. So let's say I have a field, which in my case, because I want to do random stuff in continuous spaces, is going to be RC. So, okay. Then a tensor for me will be an element of K, D, tensor P. So I hope I don't have to recall the construction of the tensor product. And what I will call a quantum state, that I will denote psi that way, will be exactly the same, KD tensor P. But then I have some kind of canonical scalar product here, and I'm going to use this canonical scalar product here to get a scalar product here, and from this scalar product I will fix the norm to be 1. Okay, so quite simple. And then the thing of interest here is
so psi and T is elements of the same space, yeah?
Sorry?
Psi and T
live in the same space. What I want to say is the quantum state is they are just tensors that have norm 1, 2 norm 1.
Okay. And the scalar product.
That's the only thing I want to say. For me, quantum state just means normalized. Okay, so nothing crazy.
Hermitian form.
Hermitian form. I mean, K will be RC, you know. So scalar product is like generic words for Hermitian form. Yeah. If you want, I can say Hermitian form, but I might slip from time to time, you know. Okay, and the thing I want to define is the injective norm. So it's a bit more general than that in practice, but in fact, but what I want to focus on is something that is relevant to quantum information. And so in this context, the injective norm of T is just the maximal overlap in KD with fixed norm xi of T with a rank 1 tensor. So is it fine? And just a scalar product of T. Take the scalar product of T or Hermitian product of T with a rank 1 tensor, and I try to maximize over rank 1 tensors. Okay? So that's the injective norm.
Will you say why it's injective?
Well, it's because actually what you use, well, it's just the same thing than for operator norm of operators and things like this. What you use is the fact that you have a norm in KD, okay, and you inject it into KD tensor P. It's like, okay. So can I use this? This paper? Yes. Okay. Great. And so maybe some remark. So again, maybe I should say, so for quantum state, it's really the same definition, you know, of max, same thing here, and then psi x1, x2 in quantum notation, xp. Okay, quantum mechanics notation. Okay, some small remark, and why, in some sense, people got interested in this. It's because it's saying something about the geometry of your state, like where does it lie compared to the space of separable states. So really, it's really this injective norm. If you compute the distance of T to rank 1 tensor or separable states, you just get that square root of T2 squared plus 1 minus 2 T injective. Okay? And so maybe I can tell you about easy cases. So easy cases, which you all know and hopefully love.
Sorry, you choose this rank 1 tensors, okay, because of course they are rank 1, but when I'm looking at your distances, it's like the zero, it's like you are looking at the distance from anybody to 0, it's something like that?
So I'm looking at this. So basically I have, let's say I have my set of quantum states, you know, some sphere. I have my quantum state here, psi, okay? And inside there is a complicated variety, you know. And this variety, I mean, well, if you want, I can give you some keyword. It's Segre variety, Segre. Okay, and this d-sep is really the distance of your point, your quantum state psi, to this Segre variety, which is the closest point of in this variety.
Okay. And these are decomposable tensors.
Yeah, they are decomposable tensors, and they are like decomposable, separable, rank 1. Like that's the 3 names for them. And so something that you know is like let p equal 1. So in that case, p equal 1, the injective norm of T, well, it's super easy. Just the 2 norm of T. Okay. And now p equal 2, something that you know also is that the injective norm of T now is a matrix, okay? And it's just the operator norm of T, which you obtained via courant feature. Okay? So those are cases that you know, and this injective norm is just a natural generalization of those two things. Okay, so proof, I don't think you need it. And then, so the main result, can I go? Oh yeah, perfect. And the model, so I told you I'm gonna look at the injective norm of those random tensors and random quantum states. So I have to say what I mean by random, okay? So maybe and main result. Okay, so in fact, my choice of randomness is quite constrained by the techniques I will be using. And so that's why I'm not picking them like for, I mean, I have reason to pick them. So the first model that I will use is that T is a Gaussian tensor, and I will call it a standard Gaussian tensor. By which I mean that the entries of T in a basis are distributed as Gaussian, standard Gaussian. Okay, so standard Gaussian really depends on the field. And then what I mean by random quantum state is like uniform states. Okay. And so, in fact, some very simple relation between these two is that if I pick T standard Gaussian tensor, then psi call in law T over T2. Okay, I have to turn the page. Okay, so once I've said that, I can state the main result. So D Kina, which is basically a high probability bound. So let P, I will look at two regimes, one in which P is fixed, and I will send D to infinity, which in quantum information corresponds to sending the local dimension to infinity while keeping the number of subsystem fixed. And then I have this quantity that I call E0P, which is the unique positive solution to an equation that is completely explicit, but I won't write everything. Solution 2 P minus 1 over 2 minus T squared over 2 plus omega of T square root of P minus 1 over P equals 0. Okay? And so what you need to know, so for expert, this omega of X is the log potential of the standard semicircular law. And for non-experts, you just know that this is piecewise function. You know, if X is smaller than, absolute value of X is smaller than 2, then you have some simple expression, which I don't remember, but basically depends on X squared. And if X is bigger in absolute value, then you have another expression, which is basically combination of logs and square roots. Okay? And so once all of this is fixed, you set alpha p for simplicity, which is just square root of p is 0p. And the claim is that the lim sup when d goes to infinity of 1 over d log probability that the injective norm of t is greater than square root of, it's pd minus 1 alpha p plus epsilon, strictly smaller than 0. And you have the lim sup, same thing, 1 over d log p. Same thing, but for quantum state. Sorry, it's not the minus 1. You don't need the minus 1. You don't need the minus 1, you just need square root of d. And here is going to be 1 over dp minus 1 over 2 alpha p plus epsilon smaller than 0. So that's the first regime where d goes to infinity. And well, next one is the eraser.
Is there?
Oh yeah, great. Thank you. And for the second regime, I fix d greater or equal to 2, fixed. Okay.
Some inequality, but does it say, do you mean to say that it's typically that this d injective will be square root of d? Yeah?
No, that's something I'm working on currently. Thank you. For now, what I can tell is that
some inequality, it's not really...
For now, with high probability, this thing is smaller than this value. Okay? And same here. And what we are doing right now is showing that you get the lower bound as well. Okay? But it's not done yet, so not talking about it. Okay, and so you have this gamma dkp, which is implicitly defined. Something. Oh, okay, great. I try to write from afar. Fine. But you know some stuff about it. You know, it gave me gamma p, sorry, behaves when p goes to infinity as square root of log p. Well, you can go up to some order, so I'm giving you the first few terms. Log p over 2 square root of log p plus beta k d square root of log p. This is explicit, a small o of square root of log p. Okay, and again, for all epsilon bigger than 0, you look at the log probability and you get in sup p goes to infinity 1 over p log probability and so this time I need the d minus 1 p d minus 1 gamma kd okay, and similarly for quantum states. Square root of p d minus 1 over dp, okay. Well, and basically it's the same thing here, smaller than 0.
Beta k d, is it a constant?
Yes, yes. It's explicit, it depends on d. Yeah, you can compute it. Just don't remember, and I didn't write it in the notes. Okay, so maybe, well, maybe it's too abstract, or maybe it's not enough, I don't know. So let's go on the less abstraction side and just compute a few cases. So something I can tell you is that alpha for p equal 2, well, I told you for p equal 2 is just the injective norm of the injective norm of tensor is just the operator norm, and so it happens that standard Gaussian tensor for p equal 2 is just a standard Genib random matrix. And so what I'm claiming is that in this case it's 2, which, well, we are very happy about because it's known that in the Genib case the operator norm should be 2. And for p equals 3, well, it's some number, you know. It has to be bigger than 2 because it's Sempian lemma, but it's some number. Okay. Well, I didn't write really well, so I'm not sure it's a 0 here, but. No. I mean, the equation is. What could you say? I mean, the equation, it has to be a 0 of some equation, which I showed, partly showed here. So then what could you say? You have log, you have square root. Probably cannot say much. And so some remark, what was known before. Well, what was known before is basically the order of magnitude of this. So you have a result of 2014 by Tomioka and Suzuki, which is saying that the injective norm of T is big O of square root dp by P. And they do that using epsilon net argument. Okay, and well, to be fair, they have T I1 IP, which are IID sub-Gaussian. Okay. So there is that, and then I think in 2009, there were some people from the quantum information community, so Flamien, Gross, Eisert, for d equal 2, they've shown that this injective norm of psi, well, is exactly what you expect given what I told you. O of square root p log p over 2p minus 1. Okay. And by the way, they also use epsilon net.
Stéphane, can you explain us what you have there in probability? So you mainly want to know the injective norm, and you say this is more okay.
So what I'm so what I'm saying, you know, if I will informally, if you want. So it's actually quite simple. Is that what I'm saying is that in both regime, like so, let's say when d goes to infinity, you know, the injective norm of t is smaller or equal to alpha of p with high probability. So it really means that the probability that the injective norm is bigger than this value is just going to 0. And I can tell you it's going exponentially fast to 0. With d. And the same is, I mean, it's the same statement for p. Instead of alpha p, you have this gamma kd of p. Okay.
So you mean that at that moment it doesn't depend anymore on d?
No. It depends on p. And here it depends on p. Then here, well, it depends on d because you know, you have this beta thing. The thing is really the rate at which it's going to 0 depends on to the limit of this guy, which behave as square root of log p, depends on d. Okay. And so our contribution is basically that we improved the bounds that were known before of Tomioka and Suzuki and Flamar, Gross-Isert, at least for the upper bound. And we actually think, at least in this regime, that this is tight. For this regime, it's not completely clear. Okay, so how much time do I have? Should be fine-ish. Yeah,
so
should do.
So more or less, you're saying that the square root of b should be there for the first regime, and you try to improve this the log term. Am I correct?
So what I'm trying to say, well, okay, so maybe I'll come back. Okay, so what I'm trying to say here is basically I know this. So d goes to infinity. Okay, I actually also know this. I think the square root is not going far away, far enough. Okay, so I know there is a small c and a big C like this, and what I'm telling you is C is, well, E0p. Okay, that's what I'm telling you.
So okay, so morally, T behaves like, you know, square root of dp.
Yeah.
Okay.
So what maybe something that you want to know or you'd like to know is, like, in terms of order of magnitude, this injective norm of T behaves exactly like the largest eigenvalue of a matrix. Doesn't depend on the fact that it's a tensor with more indices. Like the order of magnitude stays the same. Maybe it's something that's that you like. Okay, so the proof ingredients now, so great. Idea. So how do you do this? Well, so in fact, you can pull ideas that come from landscape complexity and statistical physics. So what you do is you are going to define a Gaussian process on a product of sphere, and this process will be ft from, so I will set k equal r here because it simplifies a lot of my notations and some technicalities. So I'm just going to set k equal r, but just remember that the idea is more or less the same with k equals c. Okay. And this is very simple. What I do is I take x equal x1 plus p, and I send it to, I'm going to normalize because it makes my life a bit easier, t minus 1, the scalar product of t with x1 tensor xp. Okay. And something that's easy to notice is that the injective norm of t is just the max, global max of f up to the square root of p d minus 1. Okay? And well, so what I really want to know with this probability is something that is called the excursion probability of my process. And there are classical techniques for this. T. And the classical techniques, they really rely on the fact that I can understand the number of critical points of this process, conditioned on the fact that f of t lives in some interval, like that I fix in advance. Okay. So what I'm doing is I define a random variable, which is crit ft of d, which is this number of points, x in s d minus 1 p, such that the gradient of f at x is 0, and f of x lives in D. For D, finite union of interval, we'll say. I mean, you don't really need this, but it's sufficient for me. So, and so, maybe I should make a small drawing. Let's say I have f, which is of this form, you know. Okay. Well, I pick D to be like this. No, not like this. Okay. And so what I can see in this case, for this realization of my process, I see that crit ftd equal 2. Okay, because I have two critical points here, which are in D. Okay, and how do I do this? Well, there is a well-known formula that doesn't apply in my case, but you don't need to know it because we prove an extension, which is called the Kac Rice formula. And this Kac Rice formula allows you to compute the average of the number of critical points of f of t. Okay. So assume you know this. Well, what is the probability that the injective norm is bigger or equal to u? Okay. Well, it's the same as saying that it's the same as the probability that this random variable counting parentheses is greater than 1. Okay? Because if the max is bigger than this, it means that there is at least one critical point here. Okay? And using Kac Rice formula and, well, using Markov inequality, it means that this is smaller than the average of critical points ft u plus infinity. Okay? So that's how you access this excursion probability for any process, actually, using the average number of critical points. Well, so then, the thing is you need to know what is this value, and so Kac Rice formula is telling you something, at least our extension is saying the same, that this average of critical point. So for me it's this, okay? It's the integral over my product, it's d minus 1 over the product of sphere of the natural volume form on this product of sphere times the average on my tensor, if you want, of the absolute value of the determinant of ft, of the Hessian of ft of x, indicator function that ft of x lives in D, condition to gradient ft of x equals 0. And finally, one term that I always forget, which is the evaluation of the density of the gradient of ft at 0. Okay, so gradient of ft at x is a random vector. Hopefully, if you have nice property for ft, it has a density. It happens that it's our case. And then you just evaluate it at 0, this density. Okay, so nothing crazy. So it looks a bit nasty, but it's not that bad. So why it's not that bad? So the idea is to realize that this thing will not depend on x. And so something that you have to show this, you have to understand the joint law of the Hessian f and the gradient. So how do you access this? Well, you start by computing the covariance of the process. Oh, sorry. Since my process is centered, it's just the mean of the product like this, and it's just 1 over p d minus 1, product over I of x I, y I. Okay? And from there, if I just differentiate with respect to x and y, then I can access the joint law of f, gradient, and Hessian. So that's what I'm doing. And one result of this is that the gradient of ft is independent from the Hessian and f. So that's great. It means I can get rid of this. And now I have this determinant of Hessian. And again, from this computation, what I can show is that, well, so once I've done this, I note that the law of t is the same as the action of a product of orthogonal group on T. And since this product of orthogonal group also has a transitive action on this space, okay, using that, I show that this doesn't depend on X. So now I'm left with a random matrix problem. Yes? Sorry?
Can I ask something? The gradient condition is the one that allows you to access criticality.
Yes.
You're dropping it now. So what's going on? Do you have any?
Yeah, it's just because I have independence. So the fact that I'm accessing criticality is still here, still here. Okay. But the thing is now this thing I can just drop because it's independent. So conditioning on a random variable that is independent doesn't do anything. Okay. Okay. So it's a random matrix problem because I have this random Hessian. And this random Hessian, since this quantity doesn't depend on the point, I can pick any point I want. So I pick the product of north pole of my product of spheres, which are basically vector x that are of the form 1, 0, 1, 0, and so on p times. And when I do this, what I see is that the law of the Hessian is something like this. So x0 I will call. It's basically minus t identity plus w, where t is n0 1 over p d minus 1. Okay, and w, let's say p equals 3 because it's easier to draw. It's a block matrix like this. Okay, and out the off-diagonal blocks here, those are G-libre, independent copies of G-libre random matrix, p minus 1 times d minus 1 times d minus 1, and those are just the transpose because it's a Hessian, so it needs to be symmetric. Okay. Okay, so, well, I mean, I know I have more time, but, where am I? So that's done.
But so far, Stéphane, story.
Yeah.
So far, none of this involved the normal, the law of T as a normal standard.
Oh yes, it does. A lot, yeah. So first, for instance, the fact that it's a Gaussian process, ft. Well, so it plays a a very important role because it means that I can access the law, the joint law of the gradient and deviation and f just by differentiating the covariance. And the fact is, it implies that those are Gaussian processes themselves, so they are also completely determined by their covariance and things like this. So it's very important. And another thing that's very important is if you want to condition, well, in general, so here we don't really care because we have independence, but the fact that we have independence actually comes a bit from Gaussianity. And otherwise, if it's not Gaussian, then let's say you have to condition, then you basically don't know how to do. Because conditioning with Gaussian is just a simple linear algebra problem, but if it's not, okay. Okay, and so I have this block random matrix. So one difficulty is how do you deal with this? So something block structure. So all this, the thing I'm going to list here are the thing I will put under the carpet, okay? But at least I'm telling you that I'm doing it. 0 blocks on the diagonal are really bad for usual techniques. Okay. But as long as D, well, okay, so it's not obvious, but what I'm telling you is as long as -2 square root of p minus 1 over p 2 square root of p minus 1 over p intersection D is the empty set, then I can deal with the proof. I can prove stuff, and I can show that basically this average of a determinant behave like what I'm going to tell you. This average of det Hessian f 1f in D. It's behaving as integral over D of dt square root of 2 pi exponential minus p d minus 1 t squared over 2. And well, here I'm cheating a lot, but okay, integral of log t minus lambda d mu lambda, where d mu lambda okay, I'm gonna probably get constant not correct, so forgive me for the constant. I'm going to put proportional, and it's going to be 4 p minus 1 over p minus lambda square. Okay. Okay, and once I'm there, so this is just my, in my big formula, this is just the determinant of the Hessian part. But as you might remember, there is this density of the gradient plus this volume factor, because I had to integrate over the product of sphere. So now everything will be about a competition between the growth of the volume and how this will be suppressing this growth. Okay. What I want to do is to find D, which I will pick of the form u plus infinity. Okay. I need to find D such that this thing, which is exponential of p d minus 1 log of volume of product of sphere well, and I need to take this guy. I have a term that's also coming from the density term, the density. So let's say log of rho of gradient, 0, times my integral formula. I put here exponential minus p d minus 1 t squared over 2 plus p d minus 1 omega of t square root of p minus 1 over p. Okay. And so the thing is, like basically via Laplace, so I'm gonna take log everywhere, 1 over p d minus 1, and same thing here. And then what I get via Laplace is that this is going to be the sup t in d of this thing that I'm going to be calling k of p, not k, f of p, plus this thing. So it's going to be sup of f of p minus t squared over 2 omega t square root of p minus 1 over p. So now let's say that this sup is negative. Okay, then the number of number of critical points will decrease exponentially fast. Okay, in d. And let's say this sup is positive. Now it increases exponentially. So what I want to find is that I want this sup to be 0. And the thing is that this thing looks like this, you know. Okay, with t, looks like something like this. Well, there is some. Okay. So there is some tc for which it's 0. And this tc is basically the injective norm of t. Okay. So all what I told you for now, it's valid for d goes to infinity. It's slightly, I mean, it's just technicalities to send p to infinity. Like you have to be a bit more careful with Laplace method. Okay.
You are 5 minutes.
I can have 5 minutes. So maybe what I can say is, for instance, I can say something about the motivation. One motivation, let's say one motivation. And, well, and maybe say something that I'm interested in. Okay, so one motivation. So why would you like to know this? So there are several, but one of them has to do with computational complexity. So let's say you have a problem, which is, so again, I don't know anything about computational complexity, but let's say you have a problem which is QMA hard. So what is QMA hard? QMA hard is analog of NP, but for what? For things that are very fashionable these days, for quantum computer. Okay? So unfortunately, you don't have a quantum computer. I mean, I don't know about you, but I don't have one. So still you have this problem. It's in QMA hard. It's an optimization problem. I mean, it's a problem in QMA hard. It's not, it doesn't have to be an optimization problem. The question is, what can you do with a terribly powerful classical computer that might give you an approximate answer to your problem? And it happens that, I think it's, I hope I'm not wrong, I think it's Garibian and Kempe. What they did is they show that if you have such a problem in QMA hard, you can design a NP hard problem, optimization problem. This one is optimization. Okay? That is such that if you find its solution, then it's giving you an approximate solution to this QMA hard problem. And the fun thing is that gives you an approximation. Okay? And the approximation ratio is the injective norm of some tensor, square, to be correct. Okay, so it can be, it's a tensor. You don't know much about it. It will be strongly dependent on the actual problem you have here. Okay, so then the question becomes, what are possible values of this injective norm? Because, well, if it's terribly small, then your approximation ratio is like really bad, and if it doesn't go too small, then your approximation ratio might be interesting. So there are two questions you can ask. What is the minimal injective norm? So it's not known. Okay. So your tensor here is normalized. So it's a quantum state, actually, if you want. Minimal injective norm. Okay, so the only thing that you know is that injective is bigger than 1 over dp minus 1 over 2. That's what you know, but you don't know if it's stacked. Finishing. And what is the typical value? Because then it tells you about typical QMA hard problem. Okay, and that's what we are working on. Okay, so Vincent, I see that you are here and you really want me to leave. So I guess I'm gonna stop here. And if you want to know more, you are welcome to ask questions.
Thank you. I want to tell a question relative to anti-commuting variable.
Ah, you mean, well, well, of course, yeah, you could ask. So all this work is about quantum states that have to do with qubits, if you want, or qdits, or whatever. You know, that's what we had in mind. But of course, you can be a bit more physically inclined and think about states of particles, and particles, they are often either fermions or bosons, you know. And so you can ask what is, and it's part of, it's one remark of our paper, what about typical bosons and typical fermions? Are fermions typically more entangled than asymmetric states? Are bosons less entangled, which is what you expect? So our current work hints that bosons are less entangled, but we only can do the real case, and it happens that the complex case for bosons is tiny bit more technical. And well, you can also ask for fermions, and so that's what I'm doing with a student whose name is Param Radpe. So there are several things that are interesting because this injective norm has some duality properties now, like the injective norm of fermions is the same, of a fermionic state is the same than the injective norm of the fermionic state of holes. So you have particle-hole dualities and things like this. But what I can tell you for now, because it's still a work in progress, is that when d goes to infinity, well, it's exactly the same thing. So T inj behave as a F inj, if you want. Okay? For d goes to infinity. For p goes to infinity, it's in progress, so I won't say anything. Yeah, and then if you are really crazy, you can ask about parastatistics, but I'm clearly not going to do it. So.
Are there further questions? If not,
Great.
our speaker again.
Thank you.